Okay, so the last part of this course involves devices, and we are specifically going to look at optoelectronic devices. So these are from chapter 8 of your reference text, and under these optoelectronic devices we are going to look at photodiodes and light emitting diodes. We are also going to look at field effect transistors, and these are described in chapter 6 of your reference text. And under field effect transistors, we are going to look at metal oxide semiconductor field effect transistors, abbreviated as MOSFETs. And we are also going to compare MOSFETs to TFTs. And TFT stands for thin film transistor. So TFTs are thin film transistors. So we'll look at the differences between MOSFETs and thin film transistors and try to understand why these are called TFTs and why the others are called MOSFETs. Okay, so let's start by looking at an overview of optoelectronic devices. So in summary, optoelectronic devices involve light sources such as LEDs, LCDs, and laser diodes. And they employ light detectors such as photoresistors, solar cells, phototransistors, and photodiodes. And like I said in the previous slide, in this chapter, we're just going to look briefly at LEDs and photodiodes. And basically most of the concept that we're going to learn in these two optoelectronic devices applies to the other devices. Also, we will see how we make solar cells, and just in summary, try to understand the part of the diode that we use to obtain solar cells. Now, photodiodes are two-terminal devices designed to respond to photon absorption. Some photodiodes have extremely high sensitivity and response speed, and in this section we shall investigate the response of p-n junctions to optical generation of electron hole pairs and discuss a few typical photodiode detectors structures. We shall also consider the very important use of junctions as solar cells, which convert absorbed light energy into useful electrical power. So we will look at LEDs, we'll look at photodetectors, and we'll also look at solar cells. Okay. Now, if you recall the total diode current that we studied in chapter 5, you'll find that the IV characteristics, the current voltage characteristics of a diode are represented by this figure here, where if you apply a positive voltage with respect to the P side of your p-n junction, which we call forward bias, so this is our forward bias, you find that current increases with increasing voltage, and the reason for that is because of diffusion. So if you have your diode at equilibrium, where you've got a barrier which is equal to V0, like that, and under forward bias you effectively lower this potential barrier, so you get something like that, and your barrier here is going to be equal to V0 minus V forward. So it's going to be lowered. And when your barrier is lowered, it means that electrons now can actually diffuse from N to P, and holes also can actually diffuse from P to N. So this is your P, this is your N. So under a forward bias, we lower the barrier by the applied forward bias, and diffusion of electrons from the N side to the P side and diffusion of holes from P to N is possible. So we've got our diffusion current. But if we reverse bias, on the other hand, we increase the barrier. So when we increase the barrier, diffusion of carriers is negligible, and we've got a very high electric field which runs from the N side to the P side, which is a built-in electric field. And the only current that we have now in the reverse condition is when we have electrons that find their way, that make it to the depletion region, and the electrons are swept to the N side, or if we have holes that make it to the depletion region and they are swept back to the P side. Remember, this is your P, this is your N. Due to this electric field, holes should go that way and electrons should go the other way. So the current here is due to carriers finding their way to the depletion region and being swept to their respective sides by the built-in field. Now you find that for electrons to be generated in the P side, it has to be done through thermal generation. So this is thermal generation of electron hole pairs, because electrons are minority carriers in the P side. So for you to have minority carriers, you can only do that by generating them. And since this is equilibrium, the only way we can generate the electron hole pairs is thermally. So we've got thermal generation of electron hole pairs, and the same applies to the P side. You've got thermal generation of electron and hole pairs. So the holes that find their way to the depletion region are generated thermally in the N side, and the electrons that find their way to the depletion region are generated thermally in the P side. And you remember we said the generation should occur about Ln and Lp from the junction. Okay, so from the junction, this should occur within Lp and Ln from the junction. Otherwise, the minority carriers, the electrons, will recombine before reaching the depletion region. And the same applies to the P, to the N side. The holes, if they are generated far away from the depletion region, they will recombine before they reach the depletion region. So they should be generated close to the depletion region, that is within Ln or Lp of the depletion region. So that's why we call this current the generation current, because it is due to the generation of minority carriers on either side. And as you can see that if you increase the reverse bias, there is no change in the current. That's understandable, because the size of this current is not dependent on how fast these carriers are going to be swept by the electric field, but rather by how many of them are going to be swept by the electric field. So this will only increase if the generation current increases. So for example, if you're at equilibrium, that means with increasing temperature, if you generate more electron hole pairs, that's the only time you're going to increase the generation current. But with bias, it's going to be independent. So this is what we discussed in the previous chapter. So the current due to the drift of minority carriers across the junction was identified as the generation current. Carriers generated within the depletion region W are separated by the junction field, electrons being collected in the N region and holes in the P region. Also, minority carriers generated thermally within a diffusion length of each side of the junction diffuse to the depletion region and are swept to the other side of the electric field. So in other words, carriers should be thermally generated within this region here, Ln on the P side, W and LP on the N side. So within this region, if you generate electron hole pairs, these electron hole pairs will contribute significantly to the generation current. So in the depletion region or in the neutral sides, but within a diffusion length of each side. And we also came up with the diode current as being equal to I0, where I0 here is the generation current, times E to the QV over KT minus 1. So now if the junction is uniformly illuminated by photons with H mu greater than EG, and at the generation rate GOP participates in this current. And remember, the generation rate is electron hole pairs per cubic centimeter per second. So the number of holes created per second within a diffusion length of the transition region on the N side is equal to the area times LP, which is the diffusion length of holes on the N side, times the generation rate. So you actually get the number of holes created per second. So this is just on the N side. So if I could just draw here for you, we've got our W there. So this is our P, this is our N, and we are saying here is LP and over there is LN. So we are just considering the holes created here, and we are saying this, the number of these holes are created per second. So we are saying the number of holes per second is equal to A LP GOP. So the number of holes created per second here, and our illumination is equal to that. So this is GOP, optical generation rate, which is what we have here. So similarly, ALN GOP electrons are created per second within Ln of XPO, and AWGOP carriers are generated within W. So if here we create ALP GOP, you can see that in the depletion region we also create AWGOP. So this is N side, this is within W, and on the P side we also create ALNGOP. So that's kind of easy to get. So the resulting current due to the collection of these optically generated carriers by the junction is simply, so if this is the number of carriers per second, if you want to charge the current is charge per second, so you simply multiply by the charge on the hole. So we are considering holes, so you simply multiply this guy by Q and you add them. Okay, so that's the total charge that you get. So if you do that, you come up with this equation here. So you've got your current due to optical generation is given by that. And if you have this, you can now get your total diode current. Now your total diode current becomes the thermal generation, right, times E QV over KT minus 1, and you also include the optical generated current. So your total diode current equation becomes this very huge thing here. So this guy here is our IOP. Okay, that's our IOP, and from previous chapters we derived our I thermal is equal to that. So that becomes your total diode current under illumination, the total diode current of an illuminated junction. So in terms of IV characteristics, you find that when you are in the dark without any illumination, you've got this equilibrium IV characteristics, and once you illuminate the diode, the reverse current increases like that. And you can see that G3, the generation rate, optical generation rate, G3 is larger than G2 is larger than G1. That's why the increase is in that direction. Okay, so now in your illuminated junction, if you short circuit the junction, you get what we call the short circuit current. And in this case, it is the current that crosses, it is the point at which your IV characteristics cross the y-axis, or the current axis. So we're talking about this point there. Now you know that in equilibrium, when you don't have any illumination on your device, then the current crosses the x-axis at 0 and the y-axis at 0. So at equilibrium, when your V is equal to 0, your I is equal to 0. Why? Because the terms of the diode equation, they cancel each other. Diffusion equals the current, the generation current. The diffusion current equals the generation current. So the two cancel each other, and the total current is equal to 0. So what we are talking about here is when we've got our PN there, and you actually short circuit your device, and in this case applied voltage is 0, but you've got a complete circuit. In that way, we are saying at equilibrium the current is 0, but if you illuminate the current, the diode, your IV characteristics actually cross the y-axis at negative values. So you've got this point there, that point there, and that point over there, and the increase is downwards in the negative direction, and you've got your G3 equal to G2 equal to G1. Remember that the G's are the optical generation rates. So if you've got a higher optical generation, then the negative current is also larger according to the size of the optical generation. And as usual, if you increase your negative bias or your reverse bias, the generation current is insensitive to the size of the applied negative bias. So if you apply a negative get voltage here, then you get, this becomes negative, or if your V is less than 0 volts to be precise, then you get a situation like that, where the current is constant with increasing reverse bias. Okay, now when there is an open circuit across the device, the current is 0, but you've got a voltage V, which is equal to VOC, where VOC is what we call the open circuit voltage, and VOC is equal to KT over Q ln IOP over IF plus 1. So you've got this open circuit voltage, and the appearance of this open circuit voltage, which is a forward voltage across the illuminated junction, is what we call the photovoltaic effect. And the equation here indicates that VO3 increases with GOP. So if your GOP increases, it means your IOP increases. But it is important to note that the limit of VOC is the equilibrium contact potential. So VOC cannot be larger than the equilibrium contact potential. And band-wise, if you want to understand VOC, you'll find that at equilibrium, your bands look like that. But if you illuminate your junction, you've got the barrier here is lowered, and it is actually lowered by VOC. So you get VQ V0 minus VOC here, and you can see that your VOC is actually the difference between the quasi Fermi level for electrons and the quasi Fermi level for holes. So that's where your VOC is. And the important thing that you should note here is that this photovoltaic effect increases with increasing optical generation rate, or the more light you shine on your device, the larger is the open circuit voltage. And from here you can see that actually there is a forward bias that occurs across a junction. So the junction in this case operates or acts as a battery. It is the one that gives power to the external circuit. So this is how solar cells work. You actually have your diode being the source of power. It provides power to the external circuit. Okay, so we can now summarize the operational modes of an illuminated junction by dividing the IV characteristics of a junction into 4 quadrants. So we call this quadrant the first one, this one is the second one, then this guy here is the third one, and the one that we have here is the fourth one. So we have these 4 quadrants, and somehow we name them anti-clockwise direction, starting from the top right quadrant, going around in anti-clockwise direction. We have 1, 2, 3, and 4. Now, depending on the intended application, photodiodes can be operated in either the 3rd or 4th quarters of its characteristics. Now, power is delivered. So this is very, very important to note that power is delivered to the device from the external circuit when the current and junction voltage are both positive or both negative. So if the current and the junction voltage are both or if both of them have the same sign, then according to the laws of electricity, it means that power is being delivered to the device or to the PN junction from an external circuit. So if we come back here now and look at our IV characteristics, you can see that in the first quadrant, the voltage is positive, the current is positive. So in this case as well, power is delivered to the device. The same applies to the third quadrant. You can see that the voltage is negative and the current is negative. So in this case as well, power is being delivered to the device from the external circuit. But now if you look at the fourth quadrant, you find that if you come to the fourth quadrant here, you find here that the current is negative. So I is negative, but your V is positive, right? So in the fourth quadrant, you can see that the junction works as a battery. The configuration of the junction here is similar to that of a battery, where you've got a positive voltage and a negative current. So in the fourth quadrant, right? No, fourth quadrant here, if you consider this point here, you can see that the junction actually provides power to the external circuit. So that's what we are saying in our notes here, that in the fourth quadrant, power is delivered from the junction to the external circuit. If the power is to be extracted from the device, as in solar cells, the fourth quadrant is used. On the other hand, in applications as a photo detector, we usually reverse bias the junction and operate it in the third quadrant. So just to summarize, let me start by erasing what I've written here for clarity. Okay, let's try to see now and try to understand how we bias our main device. So we said we have our LEDs, we've got our photodiodes, photodetectors, and we've got our solar cells. Now it's very, very important here. Okay, my pen has got some problems. Okay, so this should be solar cell. Okay, so we want to know the quadrant that we should use, or the bias conditions for our PN junction for us to achieve LED operation. And we also want to know the bias conditions for our PN junction for us to operate the PN junction as a photodetector. And we also want to know the bias conditions for our PN junction to operate as a solar cell. And by now, I think you've got some kind of an idea. Now, I will start with the simplest one. Now, LEDs, they emit light. So we are saying LEDs, they should emit light. And you all know that light emission is due to electron and holes recombining, right? You've got recombination of electrons and holes. Now, for us to have electrons and holes recombining, now if I could just draw here our PN junction, it means that you've got lots of electrons here and you've got lots of holes there, and this is N and this is P. So for you to have electron and hole pair recombination, it means that these electrons and these holes should meet somewhere, or in other words, you should inject minority carriers into the P. So you inject electrons into the P side, and electrons are minority carriers in the P side, so they will quickly recombine with the holes, the vast majority of holes in the P side, and emit light. You can have the same argument that if you inject holes to the N side, holes become minority carriers there, and you know minority carriers have a lifetime, which is tau N, and they will only diffuse in the N side for a short distance, which we call here LP. So in the P side also we have the same thing, the lifetime. So sorry, this is for holes here, so it's tau P. For electrons injected in the P side, their lifetime is tau N, and they will diffuse for a short distance, which is Ln in the P side. Or as the electrons and holes pass through the depletion region, they will recombine with holes here. So you can also have recombination within W and recombination within Ln and Lp. So I'll write that again. So in the P side, recombination occurs within Ln, or recombination can occur within the depletion region, or recombination of holes with electrons can occur in the N side within LP. So this is the largest, or the furthest that holes can diffuse in an N-type semiconductor, and this is the furthest that electrons can diffuse in the P semiconductor. So when these minority carriers now recombine with the majority carriers in the respective sides, if the electrons injected in the P side recombine with the holes in the P side, then we get light emission. Or if the holes injected into the N side recombine with the many electrons in the N side, then we got light emission. Or if the holes from the P side meet the electrons from the N side within the depletion region, then we can also have recombination and emission of light. So you can see that all this depends now on the migration of carriers from a region of higher carrier concentration to a region of lower carrier concentration. We are saying here electrons should move from N to P, holes from P to N. So this is diffusion, right? And the only thing that's stopping electrons to move from N to P is the potential barrier here is V0. Okay, so if you want to have LED operation where you've got lots of recombination of electrons and holes, you should lower this barrier, and the only way you can do that is by having a forward bias. So you remember, if you apply a forward bias, you lower this potential barrier by VF, right? So if you put a forward bias, so it's obvious that if you want to have LED characteristics, then you should forward bias. So it's in quadrant 1. That's where you have your LED operation. Now, for the photodetector, remember the photodetector detects the presence of light, right? And as we've been talking for quite some time now, shining light on a PN junction actually increases the reverse currents, right? The currents will increase like that. So if you want to operate your PN junction as a photo detector, then you have to reverse bias it. So you've got to operate it in the third quadrant here. So when there is no light, so maybe your current will be here, you would detect this kind of current. But if you illuminate this junction, your current will increase negatively to that point. So you can actually detect now the presence of light. And if you have more light, then the current will keep increasing in that direction with increasing light illumination. So if you want to have a photo detector, so your PD, your photo detector here, is operated in the third quadrant. The second quadrant, we don't have any IV characteristics, so we just ignore that. And for the last thing now are the solar cells. So for solar cells, you need to operate your PN junction as a power source. So like what we said in the beginning of this slide, that in the fourth quadrant, power is delivered from the PN junction to the external circuit. So you can clearly see here that the PN junction actually works as the battery. So it provides power to the external circuit, whereas in the other two quadrants, the third and the first quadrant, you actually need power to be delivered to your device. But in this other case, this battery is actually here. It's actually your PN junction, which is the battery, and it delivers power to the external circuit. So if we want to make a solar cell, we should bias our PN junction in the fourth quadrant when we want to make a LED. So this is our solar cell, this is our LED, and this is our photo detector. So that's how you should appreciate the PN junction. So the other thing that we should look at now are the photodetectors, and we said for the photodetectors we have to reverse bias our diode. So we've got a situation like that where this one increases with increasing illumination, okay, or increasing optical generation. So let's just say GOP. If GOP increases, the photocurrent also, the reverse current increases. So if you reverse bias, so this is 0. If you reverse bias your photodiode, you actually get make a photodetector. Now, just like in the solar cells, the important region also in your photodetector now is so if this is my P, if this is my N, and this guy here is my W, so the illumination should also be within LN on the P side and within LP on the N side. So illumination should be done within this region here, and if it's done further away, it means the minority carriers, the electrons here, will recombine before they reach the depletion region, and they will not be able to be swept by the built-in electric field there. So the width of the depletion region here is also very, very important. And just like in solar cells, you can lightly dope to one side. You can use a P minus N or a minus P N junction to increase the depletion width. But even if you do this, you will find that for photodetectors, the most important thing is the response time. So for photodetectors, so we've got two things in play here. So we've got what we call the response time, and we also have what we call sensitivity. Okay, so by increasing the width of the depletion region, yes, I can increase the sensitivity. Okay, and if I lightly dope, yes, it's more in one side, so the sensitivity goes up, but that does nothing to improve the response time. And in photodetectors, it is actually the response time that is important. So it is very, 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 very important for illumination to be in W. Okay, so if I can draw a PN junction like that, the electric field is here within that's my W there, right? You find that okay, so this doesn't show clearly what I want to express here. We just redraw that. So we just redraw this guy here. So I'm saying this is W, this is P, this is N, and then this is LN, this is LP. So you'll find that the carriers, they move to that region by diffusion. Okay, they also move to there. So these are electrons and these are holes. They'll move by diffusion, and once they are in the depletion region, they drift because there's an electric field here, so they're going to drift. So you've got an electric field there. So they will drift due to an electric field. So you can see that in terms of response time, generation of carriers in Ln and Lp is bad for response time. So if you generate in Lp and Ln, that's very bad because diffusion is very, very slow. So you don't want to generate a lot of carriers in Ln and Lp. So you need to generate everything within W for your detector to respond quickly to the presence of the light, because the carriers generated in W are swept by the electric field and the drift current is very fast. So it's a very fast process compared to diffusion. So you want all your generation to occur within W. So the one way to do that is to use a PIN junction. So you've got your P, and between your P and N you put an intrinsic material there. So you've got a PII stands for intrinsic. So the one that is undoped. In simple terms, the semiconductor that is undoped, and then on either side you put a P or an N. And it so happens that the high electric field present in the depletion region causes generated carriers to separate and be located across the reverse bias junction. This gives rise to current flow in an external circuit known as the photocurrent. So this is how the photodetectors work. But now when you have a PIN junction, you get a situation like this one. You can see that the intrinsic region, if you match the size of the thickness of the intrinsic region and the P and the N, if you do that experimentally and match them, you find that the entire intrinsic region forms the depletion region. Okay, you can see that here you've got a situation where you have more like two PN junctions connected back to back, right? So in that situation, you actually have your N, or your intrinsic region, being part of the whole depletion region. The intrinsic region is fully depleted. So that's very good in that the thickness now of your depletion region, the width of the depletion region is increased. It's equal to the width of the intrinsic region. So this is one way now to improve the speed, sensitivity and speed of your photodetector. Or in other words, you actually increase the sensitivity without affecting the response time. So the response time is going to be short, which is good. So high sensitivity and short response time. Short response time. So the shorter the response time, the better is the photodetector, because you quickly want to detect the presence of light. And one way or another, a very important way to do that is to make sure that all the generation is done within the depletion region, because in the depletion region, carriers move due to drift. They drift in the electric field. But if you generate carriers in the neutral regions within their diffusion length, they have to diffuse, and the diffusion process is slow, and therefore it is not recommended for detectors, because it's a very slow process. You need your detectors to be able to respond quickly, so the response time should be as short as possible. And one way to achieve that is to make a PIN photodiode. So if you make a PIN photodiode, let's say you start by depositing a P, and then you deposit an I, and you deposit an N. You should take special care in determining the thickness of the N region. So the thickness of these devices is very important. You can do that through device simulation, or you can determine the thickness experimentally. Then you have devices with varying thicknesses, you check their performance, and then somehow you can extrapolate and come up with the required thickness, because if the N region is too thick, it means that all the absorption is going to occur in the N region. And if you've got too much absorption, then you cannot have further absorption. So you should make sure that all the light that comes in, the majority of it goes to the intrinsic region. So the thickness of these 3 layers is very, very important in that respect. Okay, now we are going to look at light emitting diodes. When carriers are injected across a forward bias junction, the current is usually accounted for by recombination in the transition region and in the neutral regions near the junction. So we are saying if you forward bias your junction, so this is your P, this is your N, and by forward bias you put positive on the P, negative on the N, you reduce the barrier, then electrons actually and holes, they move like that, and along the way, if you have holes here, they can actually recombine, right? Or they can recombine here, so they recombine within L, N, W, and LP, just like what we've been talking about all along. So we are saying recombination occurs in the transition region and in the neutral regions near the junction. So these are LP and LN. Now, in a semiconductor with an indirect band gap, such as silicon or germanium, the recombination releases heat to the lattice. On the other hand, in a material characterized by direct recombination, considerable light may be given off from the junction under forward bias. This effect, called injection electroluminescence, provides an important application of diodes as generators of light. The use of light-emitting diodes in digital displays is well known. We've got our LED, TVs, and so on and so forth. And there are also other important applications, for example, in traffic and automotive signals and at illumination. So in most households, most indoor lighting is LED, or is being gradually changed into LEDs these days. Another important device making use of radiative recombination in forward biased p-n junction is the semiconductor laser. So this can be done in heavily doped p-n junctions, where you can actually get spontaneous recombinations that can actually be exploited in making lasers. We are not going to look at this in detail in this course. Now, for light-emitting diodes, abbreviated as LEDs, the frequency or color of the photon is governed by the band gap of the semiconductor, as given by Planck's relation. So HF is equal to EG, which is, in appropriate units, can be expressed as EG, the band gap in electron volts, is simply 1240 divided by the wavelength of the light in nanometers. Now, a very important metric of an LED is the external quantum efficiency, which is usually given by that, which is defined as the light output divided by the electrical input power. So the external quantum efficiency is the internal radiative frequency times the extraction efficiency. The internal efficiency is a function of the quality of the material and the structure and composition of the layer. So for you to measure this, you have to fabricate your device and actually measure it. So this can only, in most cases, determined by experiment. Now, defects in the material will clearly lead to a non-radiative recombination. However, even if the internal efficiency is high, not all photons are extracted from the LED. So you've got many non-ideal behaviors or components that come into play when you actually make a device in real life. So the external quantum efficiency is something that you need to determine experimentally. Now, in terms of energy bands, so we can show an LED as a PN junction, as you can see here. So if we have our PN junction under zero bias, so that is in equilibrium, you can see that you've got a barrier here, which is your V0, right? So due to this barrier, you cannot have electrons diffusing from N to P, and it's also difficult for holes to diffuse from P to N because of this barrier. But now in forward bias, the electron hole recombination is initiated when the electrons now remember, under forward bias, as you can see here, you lower the barrier. So some electrons higher up in the energy levels above the conduction band can actually now diffuse to the P side, and holes can actually diffuse to the N side. And when they do so, they can recombine within W here, or they can recombine within Ln in the P side, or within LP on the N side. So recombination occurs in these three regions. So recombination leads to photon emission if you've got a direct band gap semiconductor, and you can see that the current total diode current here, the forward current, is equal to IS times that, and the threshold voltage can be given by dividing your EG by E, and you can also see that you can express your I as that, where this parameter here is the ideality factor. So in homojunctions, carriers diffuse on average over a diffusion length Ln and Lp before they recombine. So it's very, very important for you to understand that in LEDs, recombination will occur within these three regions, Ln, Lp, and W, and you have to forward bias. So we use the first quadrant where we forward bias our PN junction for LED applications. And as we discussed in the previous chapters, if you utilize ternary or quaternary compounds, you can actually vary the band gap, and you know the emitted light is equal to the band gap. So if you can tune the band gap by varying alloy compositions in compound semiconductors, for example in aluminium, gallium arsenide, so in this guy here, if you vary the combinations, you can see here, if you vary X, the aluminum fraction, you can actually change the band gap. Okay, so up to here the band gap is direct. So within this region you can have your band gap varying from something like 1.4 to around 1.8. so that's a very large variation. So you, depending on the composition of your aluminum, you can actually tune the color that is emitted by your PN junction. So these are all important things to remember when you think of light emitting diodes.